Hello, this is Guillermo Campitelli, and this is the first video of the series of videos for the model comparison approach. Within model comparison, I'm going to explain three approaches: the error minimization approach, the maximum likelihood approach, and the Bayes factor approach. The first two are more traditional methods, and the Bayes factor is a Bayesian method. I'm going to talk about error minimization in this video, but I'm going to explain the problems of error minimization, and in future videos I'm going to drop this approach and use only maximum likelihood and the Bayes factor approach. But the reason I'm explaining, there are two reasons why I'm explaining the error minimization approach, and these are that first, it's sort of a simpler version of the maximum likelihood, so I want to show you the differences. And the second one is that when this approach is still used within the null hypothesis testing approach, so you are going to see a lot of concepts here that are used in more traditional analysis, and I want you to explain those concepts, even though we are not going to use this approach in future videos. Okay, so let's start with a case study, and in this case study will involve 5 models that we are going to compare using first the error minimization approach. Okay, so basically this study involves some measurement of how many hours per week number of students spent studying, the teaching quality they received, and their academic achievement. So in this model 0, what is we are showing the causal model is showing that we don't know what are the causes of academic achievement. Basically, the only variable or composite of variables is what we call unknown variables, presented here as a latent variable, and study hours and teaching quality are not related to academic achievement, therefore they are not causing academic achievement. So basically this model says we don't know anything about what causes academic achievement. And you may think, well, what's the point of this model? Well, it is important because any other model that we came up with has to be better than this one. If the models that we propose are not better than this one, that means that those models are really bad. Okay, so this model says that academic achievement is caused by the number of number of hours people you spend studying per week, plus some unknown variables. Model 2 says study hours is not related, rather is the teaching quality that students receive, and that would explain the academic achievement, plus some unknown variables. Model 3 says that both study hours and teaching quality independently influence academic achievement, plus some unknown variables. And model 4 has a new latent variable called knowledge, and basically what it says is that teaching quality and study hours do not directly influence academic achievement. What teaching quality and study hours produce is some knowledge in the individuals, and it's that knowledge that the individuals have is what will will cause the academic achievement. So knowledge here is a latent variable. It means that it wasn't measured on the study, but basically it mediates the relationship between study hours, teaching quality, and academic achievement, and the model is saying that it fully mediates because that's the only pathway that leads to academic achievement. Okay, so these are the 5 models that we are going to use and see which one is better at explaining the data. Okay, so these are the data. This is 300 observations, and the variables we measure are teaching quality, study hours, and academic achievement. And teaching quality is in the top graph. The mean is 77.91 with the standard deviation of 7.7. The vertical line here represents the mean. In study hours, the mean is 22.8 hours per week, and standard deviation 6.87. Finally, academic achievement, the mean is 50.61 and the standard deviation is 6.08. Okay, so these are the data. We have a bit more information about the correlation between these variables. Correlation can also be called association, and a mathematical representation of the association between variables is the coefficient R. And here we say that R, and between brackets we put the number of degrees of freedom. Gives us 0.13 is the association between teaching quality and study hours. The R coefficient takes values from -1 to 1, and 0 means no association whatsoever. 1 means perfect positive association, and -1 means perfect negative association. So in a positive association, if the values of teaching quality go up, the values of study hours will go up as well. Negative association means that if teaching quality goes up, then study hours goes down. And remember, association is different than causation. So the fact that variables are associated or correlated doesn't mean that they are causally related. So basically here the relationship shows that teaching quality and study hours is a weak association of 0.13. Remember, 0 means no association, 1 perfect association, a positive association. So teaching quality and academic achievement, the relationship is a bit stronger, 0.311. And study hours and academic achievement, a much stronger association, 0.731. Okay, so the variable knowledge is a latent variable, and in this study we created that variable by multiplying teaching quality, the values of teaching quality times the values of study hours. So for each of the 300 participants, we multiply their value in teaching quality times their value of study hours, and that is a crude measure of knowledge. Okay, so if you think about it, because we are multiplying, if you have high values of teaching quality and low values of study hours, it won't be as good as having medium values of both. So that's what a multiplication between the two variables achieves. A variable in which both variables are important, and if you have very low values in one of the variables, may not compensate as so having very high values on the other variable may not compensate as much. Okay, so basically these are now the data that we are going to use to compare the models. And as I said, we are going to use the error minimization approach. Okay, this approach involves first conducting parameter estimation in each model with the constraints determined by the models. Then use the models with the estimated parameters to make predictions of the dependent variable for each model. and use a statistic to determine the predictive error of each model, use another statistic that adjusts for the complexity of the model, and compare models based on the latter statistic. I'm going to show you these 5 steps. So first we need a statistical model. Remember, we've got the causal model as a model of the relationship between variables in the world. We need to transform that into a statistical model which uses some of the variables that are present in the causal model, but other variables or parameters are just mathematical tools which sometimes have a meaningful psychological interpretation and sometimes they don't. But they are necessary to make the calculations of the model. So this is the statistical models, which the structure of the model is the same for models 0 to model 3. Model 4 has a different structure. What it will change in models is the constraints that each model has. So here we've got that the variable SH, which is studying hours, and TQ, which is teaching quality, will affect the variable mu, and also the parameters beta 0, beta 1, beta 2 will affect and mu and sigma affect the values of academic achievement. Now this rounded rectangle, it's what we call a plate, and we call the I plate, and the I goes from 1 to 300. That means that whatever is inside, that they all have an I, a subscript I. Whatever is inside this plate, it repeats 300 times. So basically we have 300 values of study hours, 300 values of teaching quality, 300 mu's, and 300 values of academic achievement. So these are measure variables, that's why they are in dark brown, and this is a latent variable as those, that's why it's in a light color. So the variables or the parameters here are all parameters that are outside the plate, do not repeat. So basically we have only one beta 0, only one beta 1, only one beta 2, and only one sigma. And so basically what this model is saying is that the values of academic achievement are generated by the mu's plus some error. The sigma means error, and you can see that in the formula. First, we get an equation for calculating mu. So we've got 300 mu's. We multiply beta 0 times 1. So whatever the value of beta 0 we come up with, and I'm going to explain how we do that, and we have only one, and it's going to be multiplied by 1. Now the value of beta 1 that we come up with is only one value. It will be multiplied by each of the study hours values that we measured, and the same for teaching quality. All the values of teaching quality, each value of teaching quality will be multiplied by the beta 2 parameter that we obtain. So that gives us a value of 300 values of mu, or 300 mu's. And then what we say, this sign means is distributed. So basically the values of academic achievement are distributed normally, and the mean of that distribution is the the 300 mu's and 1 sigma. So basically this is saying that each score of academic achievement is like obtaining so it's like obtaining a score from a distribution, from a population of scores that are normally distributed, and the mean of that distribution is each of the mu's, and the standard deviation of that distribution is always the same, is sigma. So we have 300 normal distributions. All of these 300 distributions have different means, so we have one mean for that distribution, but all those distributions have the same standard deviation. Okay, so and that score is the academic achievement score is one score that we obtain from that distribution. Now, this explanation will become much clearer when I explain the maximum likelihood approach. So bear with me. I am conscious that the explanation is still not very clear, but it will be completed in the maximum likelihood approach. So basically, in this approach, what we have is 300. We calculate the parameters beta 0, beta 1, beta 2, and we use this formula to obtain 300 mu's. And these 300 mu's are the predictions of the model of the scores of academic achievement. Yeah. So basically, when we calculate the beta 0, beta 1, and beta 2, we have to come up with values that will try to minimize the error of the prediction. Okay, so when we calculate these parameters, we need to take into account the scores of academic achievement that we already have. So the mu values that we obtain are close to the academic achievement values, so our prediction error is small. So that's what the error minimization approach is, trying to minimize the error of the prediction of the model. Okay, now how do we calculate the beta 0, beta 1, and beta 2? Well, that's not a task for humans, it's a task for computers. So computers will calculate that for us. In some situations, the calculation of the values is using matrix algebra, and sometimes it requires some mathematical simulation. Computers are great for that, humans are really bad for that, so we leave that work to computers. Our work as humans is to try to understand what the computer is doing, not doing what they do better than us. Okay, so calculating the beta 0, beta 1, and beta 2 is not something that you have to worry about, because you are not going to do it. Okay, so but the idea is that the computer will come up with the best values of beta 0, beta 1, beta 2 to produce mu's that are close to the scores of academic achievement, and in that way reducing the error of the prediction of the model. Okay, now this is a generic structure for models 0 to 3, but models 0 to 3 are different, and they are different in the constraints. So here we have the constraints. Model 0, beta 1 is 0 and beta 2 is 0, so it's fixed. So we don't have to estimate the values of beta 1 and beta 0 because, sorry, beta 1 and beta 2 because they are fixed to 0. So beta 0 is the only parameter that is let free to vary. In model 1, beta 2 is fixed to 0, and beta 0 and beta 1 are free to vary. Model 2, beta 1 is fixed to 0, and beta 0 and beta 2 are free to vary. And in model 3, the three parameters are free to vary. Okay, so I return. Sorry, that's not the one. To come back. Okay, so I return now to the slide that I wanted to go. Basically, in model 0, this value is 0, this value is 0, and this value is free to vary. So basically, because beta 1 multiplies by SH and beta 2 multiplies by TQ, and these two values are 0, so basically none of these values are important. So beta 0 will be determining the mu's, and because beta 0 is one value, the mu's will be the same value. So the 300 mu's will have one value. Now for model 1, we fixed only beta 2 to 0. So basically it will calculate the value. So it combines beta 1 with SH, but TQ is not taken into account. Model 2 is the other way around. Beta 1 is fixed to 0 and beta 2 is free to vary. So basically teaching quality is taken into account, but not study hours. And model 3, the three parameters are free to vary, so both variables are taken into account. Okay, so these are the models and the constraints, models 0 to 3. Now model 4, it has a different structure. Basically Ki, we are going to obtain 300 values of K, which is knowledge, and they are obtained by multiplying study hours and teaching quality, and knowledge will be a new variable. And as we have in the formula, we have a beta 0 that is going to be part of the model, and beta 3. So beta 1 and 2 are not used here, and both beta 0 and beta 3 are free to vary. Now, just one minor thing. K is now not a latent variable like it was in the causal model, because in the causal model it was not measured. It's a variable that we didn't know, but in the statistical model it is a measured variable. It's not something that we are going to estimate. It's something that we calculated by combining these two, multiplying the values of SH and TQ. So that shows the importance of differentiating statistical model from the causal model. They have some similarities, but they are not the same. Okay, so basically the second part of the model is exactly the same as before. The scores of academic achievement come from from normal distributions, which with mu as the mean and sigma as standard deviation. Okay, so basically this model only takes into account the variable knowledge and not the other variables. And the constraint is the model beta 0 and beta 3 are free to vary. Beta 1 and beta 2, they are not even presented in the model. Okay, so these are the results, and the graphs here show the three panels. Show in blue each raw score. In the x-axis we've got the study hours of each participant, and in the y-axis we've got the academic achievement of each participant. The black line in the three panels always indicates the predictions of model 0. You can see that the black line the prediction for each value of study hours is the same value for academic achievement. So if you study 10 hours, our prediction is around 50 of academic achievement. If you study 20 hours, the prediction is the same. If you study 30 hours, the prediction is exactly the same. So that's model 0, in which none of the other variables is taken into account and is shown in the 3 panels. Now the green line is model 1, and model 1, it's the prediction of academic achievement takes into account only study hours. So we've got the green line, and as you can see, the green line captures the pattern of the data, so this upward trend. Now maybe we can come up with a better model than model 1, but it's a decent model that captures the trend of the data. Now model 1 is presented in the 3 panels as a green line. Now the red lines or curves, better, more appropriately, they represent different models in each panel. So in the top panel, the red line represents model 2. In the middle panel, the red line represents model 3, and in the bottom panel, the red line curve represents model 4. So one thing that I have to warn you in this graph is that these curves they look like a very complex model. In fact, they are not very complex models. They are simple models, but because I'm showing you the data related only using the variable study hours and academic achievement, then these curves look like very complex. But if I used the other variables that are used in each of those models, then there will be a line. So it's not a complex model. So the reason that the models appear complex is because I chose to present the graphs with only study hours and academic achievement. Now so we can see that the green line captures the trend of the data, so it's a decent model. Now what we can also say is that model 2 is really bad, because you can see that model 2 it goes up and down, but crossing the black line, so it doesn't capture any of the variability of the data. So it doesn't capture the trend of the data at all. Now in models 2, in the middle panel, which is model 3, as you can see, it is up and down but crossing the green line, so basically it captures the trend of the data. Now we don't know by visual inspection whether it is a better model than model 1 or not. We know that it's better than model 0, but we cannot say anything about the difference between model 1 and model 3. Model 4 the same, it captures the trend of the data, but again visually we cannot say anything if it captures if it's better than model 1 or not. So in order to do that, we need some numerical analysis to determine which model better captures the data or predicts the data. Okay, so here we've got a table with the values of the parameters estimated and some goodness of fit statistics. So basically for model 0, the best parameter for beta 0, the best value for the parameter beta 0 is 50.61. And as we indicated, beta 1 and beta 2 were fixed to 0. There was no estimation. Beta 3 was not even in the model. We've got an indication of degrees of freedom. And then this is a very important concept, this sum of squares error. Sum of square errors is calculated in a very simple way. It takes into account the prediction of the model for each score of academic achievement, and it subtracts the actual score of academic achievement. So we've got 300 scores of academic achievement and 300 predictions for each of those scores. Sorry, and one prediction for each of those scores, so we've got 300 predictions. So we subtract the predictions from the actual value, or the other way around, and you'll see that it's going to be the same. And then that difference between the prediction and the actual score is squared. So sometimes the difference is positive, sometimes it's negative. So, but when we square two positive values, so when we multiply two positive values, we will get a positive value, and when we multiply two negative numbers, we get a positive number. So basically we get rid of all the negative values. So we've got 300 squares values, and what we have to do is to sum those, and that's the sum of square error of the model. So basically model 0, that value is 11,076. This means that the model 0, the predictions, the error of the predictions, they sum to 11,076. Now the MSE is mean square error, which is a mean of that. So basically what it does is to divide 11,076 divided by 299, the number of degrees of freedom, and that's 37.04. So basically this 37.04 tells you, well, it's more or less for each prediction we got 37 points of difference to the actual score. That's on average. But because these scores come from a square scores, it wouldn't be very representative. So the RMSE is root mean square error. Root means square error. So basically it's the square root of that. So if we use squared values to calculate the mean square error, we obtain the square root of 37.04, and that is a better in terms of a more intuitive score that tells us that there were 6.08 points of error on average for each prediction. Okay, so basically we don't need all these all these values. We sometimes need those values to calculate other scores that we are not using here, but so they are typically reported, but they provide more or less the same information. Okay, so that is model 0, but remember, model 0 we want it as a model that the other models have to be better than this one. Now the R square is basically the variability of academics, the variable academic achievement, how much of that is accounted for the model. And in this case it's 0, because basically there is obtain the sum of square error of the academic achievement, it will be exactly the same, because the way you calculate it is, remember, when you calculate the variance or the standard deviation of any variable, you subtract each value from the mean, and in this case beta 0, the best value of beta 0 is the mean of academic achievement. So basically the model 0 explains 0 of the variance of academic achievement. Now the other models have to explain as much as they can of these 11,076 sum of square errors. Okay, model 1, the best score for beta 0 is 35.82. The best one for beta 1 is 0.648. So we used that mathematical formula that I showed you before in order to calculate the mu's, which are the predictions, and then these mu's are subtracted from the actual academic achievement scores, and then those scores are squared, and then they are added up, and we get a prediction, a sum of the errors, and that is 5,151. So basically that is what is not explained of this variability by model 1. So basically model 1 explains 11,076 minus 5,151 of the variance. So if you calculate 11,076 minus 5,151, that's 5,925. So 5,925 is the variability that the model 1 explains, and 5,151 is the variability it doesn't explain. So if you calculate the variability that it explains, 5,925 divided by the total variability, 11,076, that is 0.535. That's the R square. Yes, so 11,076 minus this value, and that the score we obtain there, we divide by 11,076, and that's the R square. So basically the R square tells us how much of the variability of the data is explained by the model. Okay, so this is more than half. Okay, so basically this mean square error and root mean square error are calculated in the same way as in model 0. Here we've got the values of model 2. As we said before, beta 1 is fixed to 0, beta 2 is free to vary, so we have the score, and then it's got quite much more error than model 1. And you see it's not that far from 11,000, so it's not explaining very much. Actually, the R square is 0.097. Not very good. Model 3, remember we didn't know whether model 3 was better than model 1 by visual inspection, but now we can see that it is better, because the error is smaller and the R square is higher, so it explains more of the variability. And model 4 is a bit better than model 1, but a bit worse than model 3, so the R square is a bit smaller. Now, what's adjusted R square? Well, remember that one of the steps was to adjust for complexity. So the models that have more parameters are more complex models, and we want to avoid one thing that is called overfitting, and overfitting is done when we have very complex models with a lot of parameters. And so basically, in order to penalize for the parameters we put into a model, we use the adjusted square, and the adjusted square it's a formula that uses the r-square and penalizes for the parameters used. So 0.535 becomes 0.533, 0.097 becomes 0.094, 0.583 becomes 0.580, and 0.573 becomes 0.572. So still model 3 is the one that explains more of the variability of the data. Okay, so we need a procedure to compare the models now, because we have this r-square of each model, and it tells how much variability is explained by the model, but we don't have an idea to say, okay, this one which model, if the differences in the variability that is explained by each model is significant or not. So the traditional methods want to come up with a p-value in order to see which model is best. Okay, so this approach allows us to do this when the models are nested. Now, nested models are models in which one model is a bit complex than the other, and if you take one parameter of that model, you get the simpler model, and that some of the models here in this case are nested and some of the models are not nested. Okay, so I'm going to do the model comparison for nested models and show you which ones are not nested. So basically the procedure is the following. We've got the sum of square errors of model 0 here, 11,076, with degrees of freedom 299. The sum of square error of model 1, 5,151, with degrees of freedom 298. So what we have to do is the difference between these two and the difference between these two. So the difference between 11,076 and 5,151 is 5,925. And the difference between 299 and 298 is 1. So basically we've got this score and with these degrees of freedom. Well, there is a test which is called a distribution, the chi-square distribution, and which determines how likely is to obtain this value from a population in which the difference between the sum of square errors is 0. So maybe in the population the sum of square errors is 0, the difference is 0, but here in our sample, just by chance, we obtain a very peculiar sample of that population that gives us huge difference. Well, how likely is that? Well, the chi-square distribution is the sampling distribution that we use in this case. And how likely is that? Very unlikely. It's very, very unlikely, almost impossible. So we determine that model 1 explains more variance than model 0, because it's very unlikely that they come from a population in which the variance explained by model 1 and the variance explained by model 0 is exactly the same. Okay, so that's the procedure to compare the models. Now we can compare model 0 and model 1 because model 0 had the beta 0 only, and model 1 had beta 0 and beta 1. So we get rid of beta 1 and we have model 0. So these models are nested. So model 0 versus model 2 again, because the difference is beta 2. If we get rid of beta 2 in model 2, we obtain model 0. We do exactly the same. Sum of square errors of model 0 and sum of square of model 2 and the degrees of freedom. So we obtain a difference of 1072 and degrees of freedom difference 1. Still, it's very unlikely that they come from a population in which the variance explained by these models is the same. So again, we say that model 2 is better than model 0. Model 3 can be also compared with model 0, because model 3 has beta 1 and beta 2, and if we get rid of beta 1 and beta 2, we get is the same as model 0, therefore they are nested. And we do exactly the same procedure. Now the difference is 2 degrees of freedom, and we've got this score, and again in the distribution it's very unlikely that this difference comes from a population in which the models explain the same amount of variance. Again, we can compare model 0 with model 4, because model 0 has beta 0 and model 4 has beta 0 and beta 3. If we get rid of beta 3, then we obtain betas. We've got the same model. Now the difference is 351, and the difference in degrees of freedom is 1. Again, very unlikely. Now we can compare another two models, model 1 and model 3, because model 1 has beta 0 and beta 1, model 3 has beta 0, beta 1 and beta 2. So we'll get rid of beta 2 and we'll obtain model 1. So they are nested. The difference is 527 with 1 degree of freedom, and again that's very unlikely. So basically model 3 is better than model 1. Now the problem of this approach is that there are models that we cannot compare. Model 2 and model 3 cannot be compared. It is model 1 and model 2 the ones who cannot be compared, because model 1 contains a beta 0 and a beta 1, model 2 a beta 0 and beta 2. So there is no way that getting rid of one of the parameters we get the other model. Same with model 1 and model 4. Model 1 has beta 0 and beta 1, and model 4 has beta 0 and beta 3. So again, we cannot get rid of beta 3 and get model 1, because model 1 has a beta 1. And same with model 2 and model 4. Model 2 has beta 0 and beta 2, and model 4 beta 0 and beta 3. So again, not nested. So we cannot use this error minimization approach. So in order to be able to compare non-nested models, we need to use the maximum likelihood approach, which I will explain in the next video.